I will start by presenting myself a little bit to try and understand who am I and what I am doing. The more formal part, I'm a full professor since 2013 in France at the ETIS Lab. The ETIS Lab is a UMR, which is a mixed research unit between the university, the CY Cergy Paris University that I am, and CA, that is one of the grand écoles in France in engineering, and CNRS, which is the national research institution that runs the majority of the research in France and supervises it as well. And generally in France, having the CNRS label is a label of quality and excellence in research. I'm a member of the data and artificial intelligence team of the lab. I was the previous director of the team until 2020. And besides my research activities, I am also responsible. I am directing two masters that we have, one in data science and machine learning and one in data engineering for intelligent and distributed systems. I'm also running a master in data science for non-computer scientists that we've discussed also a couple of times as well. And I'm also running two double degrees in data science, one with Just University in China and one with the University of Mauritius in Mauritius. So besides my, let's say, research activities that we will talk more, I'm trying to be active also in the educational part. Which also means that I am teaching a few courses. Just to give you an idea, I'm teaching courses in the bachelor, one called Introduction to Data Science and another one in mobile computing. And the majority of my teaching is in the master's level. I'm teaching cloud computing, distributed systems, data mining and machine learning, databases. Also, transparency and fairness for AI models, which is quite new course. And I'm teaching in other master programs as well, like the master in physics, master in chemistry, and also a master's in political science, where I'm teaching this course that I have highlighted on data protection and digital tools, where we are discussing, among other things, issues on privacy, on fairness of data analysis and of disinformation, where we are using also some of the work that we did in the Erasmus Plus project that we have with Eleni. Okay, sorry for the long personal rambling, but I think it's good to have just an overview. So today I'm going to touch different things which do not necessarily overlap and do not necessarily everything fits together, but okay, at least in my mind, there is a bigger plan, so somehow it fits. So what I'm gonna talk, I will start by discussing problems in the area that we generally call data reduction, which is kind of the inverse problem that we usually have. Usually we don't have enough data to work with, but sometimes we have too much data to work with and we want to reduce them, but we want to reduce them in a way that makes sense. Okay, so we don't want to delete all words that start from A, for example, right? We need to keep a distribution that makes sense somehow. And this becomes a more difficult problem when we introduce semantics into the mix. Then I'm going to discuss a work that we did around sentiment analysis, where I'm going to show the solution that we employed and the experiments we did for real time, so on the spot, as for example, a post arrives on social media or offline sentiment analysis. and discuss different methods and issues that we faced there. I'm going to give you a little overview of another work that I suppose it's interesting for you, which has to do on how we try to track the changes in the political landscape discussions before election periods, and try to understand, for example, if results that were a surprise were actually there before we saw them in the voting results. I'm going to talk a bit about a more, let's say, computational work that has to do with AI and explainability. So how we can provide explanations on why or why not our AI models gave us a result or not. Okay. And I'm going to present a few research projects that I'm currently working on, which kind of give what are my plans also for the future in terms of research. A lot of those things that I'm going to discuss have to do with graphs. Okay, so one of the things that has somehow a common line to a lot of those works is working with data that have some kind of explicit or implicit graph structure. Okay. Again, feel free to stop me if something is not clear. I'll try to provide examples as much as possible, but again, if something is missing, say so. Okay, so let's start with the first issue that I would like to raise with you, which is how we can work with large knowledge graphs without actually having to work with this kind of large knowledge graphs all the time. The overall problem, okay, starts from the fact that we have, as you know, linked open data, which are bringing together different knowledge graphs. So at the end, we have a very large and connected structure that we need to query, okay, to ask questions on it, to find what we are looking for, to visualize, or in general explore. So one question that needs to be answered is, how can we do that in a way that on the one hand will be possible? For example, we don't want to visualize something like what you see on the right-hand side of the screen because we cannot really see anything, right? Useful at least. On the other hand, we don't want to spend computational resources to query various different parts of the knowledge graphs. If those knowledge graphs we can test and we can find out that they do not contain any useful information. So imagine, for example, a knowledge graph that gives you 1 million answers for your question, and another knowledge graph that gives you one answer to your question. If both are equally large, then asking the second knowledge graph for the information is useless, right? Because I add just one piece to the 1 million other pieces that we have, but the cost to get the one piece is equal to the cost that you pay to get the 1 million. So the question is, can we avoid that in a way that we don't lose at the same time important information? So higher size, higher complexity in knowledge graphs. How we can reduce that to something that is more manageable, let's say in general. Okay. Knowledge graphs, I suppose that more or less everybody knows, but I'm going just to make a point to make sure that we are in the same context. Knowledge graphs are usually represented in what we call the RDF language, which describes information in the form of triples, like what you see on the slide, or in the form of graphs, if we want to see it graphically, and basically uses an ontology that allows us to describe our resources, and based on that, we can unify, we can ask queries, okay, and so on. RDF comes with some standard notions, so defines some common things. For example, it defines what is a class, which represents basically, and sorry for abstracting a bit, but basically represents concept, properties that represent relationships, and then what we call also subsumption, so hierarchical relationships between concepts, right? So class and subclass and properties, okay, property and sub-property, and more. Okay, so the formalities is another thing. I will not go into that. I think it's enough. So what we have is something like what you see. We have a schema, which is usually an ontology, where we describe the main concepts and the relationships between the concepts. And then we have our data, our instances, where we associate them with the concepts, with the classes, and we use the properties to describe the connections. And actually, what we want to have is the ability to query our resources, right? So for example, this is a very primitive ontology to describe music and records and artists. If we want to find out which records were made by Celine Dion and I don't know, whatever preferable artist you have, we can do that and get back results. So basically, the idea is that we would like to be able to use the ontology, so something general and, if possible, standardized, to query our data and find what we are looking for. Okay. So this can become quite large, okay, especially the part of the data, the part of the instances. If we imagine that we use that to describe all the music industry, right? And now the issue is that we don't want to do that all the time. So what we would like to have is something that is definitely smaller than the original part, contains still the important information, and how we define importance can be case specific as well. And at the end also, if possible, produces also a similar RDF graph, a similar knowledge graph. And we like that because we still like to use the same tools to query that. Also, what we would like to have is to be independent from the schema, because we have knowledge graphs that do not necessarily have one ontology attached, or they might have more than ones. Would work in heterogeneous environments. Again, we might have data being described with different ontologies, different schemas, and give us some idea of measuring importance, for example, through statistical information. Not the first work done in the area, but the work that I'm going to present gives us the best results with some affordances as far as we know. Okay. If interested, we have a very extended review paper on those methods that you can have a look at. So what we did is that we proposed an algorithm. We will not go into the formalities again, but just into the general idea, which takes a knowledge graph, transforms it in a binary matrix. A binary matrix is a two-dimensional table with zeros and ones. I'll show an example right after. Uses an algorithm that does what we call approximate pattern mining, and then reconstructs the summary graph from the results. Okay. So the binary matrix is the transformation of the graph to zeros and ones, which is something that in computer science we like a lot, because we love zeros and ones, because everything is zeros and ones, right, at the end. So in reality, what's the benefit here is that we simplify a lot of the representation for what we want to do. And at the same time, we can compress it quite a lot, so we can work with larger graphs, because zeros and ones can be easily compressed as bits, not bytes. Okay. So how do we work? We take a part of the graph, we transform the connections to zero and ones. For example, we are saying that Celine Dion as an object, okay, is using a connection that says that is a music artist, right? If you see there, there is a type connection on the top. Uses the image property, uses the name property, uses the biography property, okay, uses the mate property, and so on. So we do that for all our instances, which could be millions or billions, right? So the rows could extend to millions or billions. The columns are all the different properties that we could have in our graph. Then we do that for everything, right? So we do that here, okay, and so on and so on. And then we go on to work on this binary matrix to find our patterns, right? What is a pattern is something that repeats itself many times. And the idea is that if something repeats itself many times, then it's important, right? Because it somehow appears a lot, so we can use it to describe our graph. Okay. Now, I press OK.
Because we cannot see the first
Yeah.
line.
Okay, sorry.
Thank you so much. We need your consent.
If I manage to click it, you'll get it, but consent is difficult. No, I cannot do it. No.
That's why I love touch screens and I don't use Mac. Sorry.
Okay. Extreme measures.
Sorry. It was
No, but thank you for pointing that out. But I need to reshare that now, I think. Right, Rafael, I need to reshare. Okay. Sorry online for the interruption. Okay, it's good. Okay. Okay, so okay. So as I was saying, a pattern is something that repeats a lot, and this is what we consider important as to be present in the summary. The other thing that I need to point out is that we are doing approximate pattern mining, which means that we are flexible, right? So we are relaxed. And we do that by introducing what we call a cost function. Again, we don't go into the mathematics, but the idea here is that, as you will see, if we find an error and we want to accept the error, we penalize it somehow. So this allows us to accept more. So, example here, okay, you see that there is a repetition there, right? So for these three objects, these three instances, we have the same properties used, right? So somehow we can use that at the end, right, to assume that these objects are under the same class without having any information about the class at all. We don't care, okay? So what we want though to do is to get as many properties as possible in the summary, because this enriches our description. So in order to do that, we try then to add additional properties, for example, the property biography, right? So what we do is that we accept biography by somehow correcting the zero that was there, if you remember, right? And while it's not fully in the pattern as the previous properties, we accept it and we penalize ourselves. So instead of counting there, if you put everything together, 15 ones, right? I count 14 ones. Before, right, in the previous case here, we had 12 ones, right? So the idea is that as long as our additions improve our score, we accept them. If they start penalizing us too much, we stop accepting. Okay. Now, what's the basic problem that we have here is that this is what we call a greedy algorithm because we have to do all possible comparisons for all permutations, both for the lines and for the columns that we have. So if we have millions or billions of lines, which is usually the large part, okay, this is something computationally expensive. Okay. Okay. Assuming that we find those patterns, then we try to bring them together. So we have the first pattern that is described by the properties that we found. We try to join that with the second pattern if they share a property, for example. Then this pattern has its own properties, and like that, we build a summary graph. Okay. The summary graph, depending on the case, not all the time, so we cannot formally prove that, but most of the times, can give us also the ability of an ontology that is used, even if the ontology was not there. So we can use this also for what we call ontology extraction problems. Again, this will give us only those parts of the ontology that are used extensively in our knowledge graph. But in most of the cases, this is sufficient, right? So we don't care usually if I have a knowledge graph with millions of instances. I don't care if one instance is using one property only, right? So we don't care about that. We can forget it, let's say. Okay, but again, that depends on our problem. We did some experiments, not to bother you too much of that, to brag that we have the best results and so on. We do, but that's one of the things. One other thing is that if this matrix that we have grows too much, sometimes might not fit in memory. So, for example, DBpedia, which is the knowledge graph of Wikipedia, right, represents Wikipedia as a knowledge graph, is too big to fit in memory. So this drove us to find other solutions. I'll make a point next. Okay. But in general, we have good results and also some experiments in the sense that we are getting better quality summaries compared to the other algorithms that we have. So for those cases that the data is, the knowledge graph is too big, we have a parallel distributed implementation of the algorithm that uses cloud to distribute the data and the computation. Again, the fact that we are working with approximate patterns helps because we can use this cost function, the penalization that I described before, to do that in a parallelized way. So we can work through whatever size of knowledge graphs we have. I will not go again into the implementation details. A note about the quality. So part of the work that we did, which was the main part of the PhD of a student of mine, is to propose also a quality framework to be able to compare two summaries. One of the problems that we have in this case, in general, is the fact that we don't have what we call a ground truth. There is no way to say that this is, let's say, the best summary ever, because what is the best summary depends on the application that you have. So if you want to visualize, it could be different than if you want to query. Okay. So what we did there was not to say what is the best, but to give the tools, the metrics, to be able to compare to, and then you can make your choice. And this was quite detailed because we tried to compare at the schema level. Okay, so what are the classes and properties that were found? Also at the instance level, how well two summaries represent my original knowledge graph, and also how well connected the results are, because usually we like to have a summary that is connected and not bits and bytes, okay, pieces overall. Okay. So we propose different metrics. Again, I mean, if someone is interested, please ask, and I can provide details, but for time, I will skip through. Okay, so we have different metrics provided, and we experimented to compare that. So, for example, other algorithms give you a summary like that. For example, here, the problem that we have is that is not really a connected summary, and also it's very verbose, so it uses many different parts to describe the same thing, right? So what, for example, later on you will see we describe as, so this is our solution. We'll describe it as one thing, right? This is described with 6, okay, so, okay. But we also did, let's say, analytical evaluation. So we have metrics that give us precise information on where one summary is better than the other, and so on. Okay. Again, I'm not talking about the results, but they are there. One issue that I forgot also to mention that is important is that what we proposed work equally well if we have a knowledge graph that has already a schema or that does not have a schema at all. So we have equally good results, which is not usually the case in most of the algorithms that exist. Okay. So to sum up this part, we try to work into providing summaries which are actually customizable, because we can change the cost function as we like. So we can provide also personalized summaries if someone wants to have something specific. We try to solve the problem of speed and memory by providing distributed versions that are scalable. And we also produced a way to evaluate the quality of the summaries that we have. Of course, it's not finished, so if someone still wants to work on it, I'm happy to collaborate. For example, one issue that is still pending, and Christophe will relate to that, I'm sure, is that is extremely difficult to work, and we get problems if we have a very dense hierarchy. So hierarchical relationships, because they are hierarchical and the instances might belong to all the classes in hierarchy, are very difficult to capture in some cases. Also, we might need to provide preferential treatment for different relationships, to say, for example, that, look, this relationship, I definitely want it to be in the summary, regardless if it's important or not, okay? And other points like that. And recently, we started also looking into solutions that use graph neural networks to do that, but that's not something that I can present yet. Okay, and okay, we had a couple of publications out of that, so also if you are interested in looking more, Okay, so questions on that? Because that's just the first part, and we have other 5.
I have a question
Yep,
about
please.
that you explain about the algorithm, because you need to choose parts of the graph in order to model the matrix.
No, I take all the graph and I transform it to the matrix.
The matrix, I mean.
I start with a line and I'm looking in the neighborhood. Okay.
So do you overlap those lines.
What do you mean by overlap?
That was Celine Dion, I don't know from,
Yeah, I can.
it was maybe one of the first ones.
Yeah.
Here, like for example, if you have another one where you make a square around it, like.
Yep.
No, the one over the graph, sorry.
The one with?
This one.
Okay.
This
Oh,
one,
it's
so
cool.
for choosing, for example, the first one, it is Celine Dion, which
Yep.
is the square up in the graph, I think. So for example, you don't evaluate that part of the graph for any other line, right?
What do you mean by evaluate?
You get that first line from.
So I get the
square.
first line. Okay, to become a pattern, I need to have other lines that have ones in the same place. Okay, so what I do is that I compare this line then with the next line and the next line and the next line and the next line, all the lines that I have in the matrix. Yes, I'm interested in the ones because the ones means that something exists there. The zero means that I don't have the connection.
And the order of the columns doesn't matter or not?
It doesn't because, as I said, I do all the permutations possible. And that's why it's very expensive computationally.
Yeah.
And I do all the permutations, not only for the columns, but also for the lines.
But it is some overlapping in the matrix, right? Because if you get the other node, the one on the right,
Mhm.
you are sure that you are going to have overlapping between that lines, the main line. For example, the relationship will overlap.
Yes, if they overlap, the relation will appear
But
in.
The relation later. You don't do any reduction in the.
No, I don't want to do any reduction. And this is because later on, okay, if it overlaps, right, it will appear in both patterns, and I'm going to use this to connect the patterns, so I will have my connected graph. So actually, overlaps between patterns in that respect are very useful. Okay. Something else?
Yes, just it's very, I think it's very interesting, mainly when you have not an ontology. I mean that you have no formal specification of class, because in this case it's very useful, no specification of object property too. So for building or extracting ontology from text is quite useful, because you can start from a corpus one, you can build an RDF graph, and since we don't know, you have no formal definition of classes, neither for properties, is very, very interesting. Of course, if you have already a good ontology with formal specification, knowing the object property restrictions, domain and range of properties, you have already. It's a slide 28. It's very interesting. Yes, in the case where I don't know the structure, I don't know the classes, I don't know the properties. Of course, you have already one, pattern one. It's auto. You have already.
Yeah, and then of course you might, depending on the information that is there, you might need to intervene to, if you want to give a meaningful name, for example, in pattern one, because I cannot really name the class, right? Because that's part of the formal definition of the ontology that should come.
Perhaps I don't know, we can more or less introduce new parameters. For example, I know that for these relationships, I know the domain and range in order to
that you know, because you have the RDF part, right? But if this domain and range is actually an instance of a class, okay, that might not be there at all. So it depends. But if you have this type of information, could also be used like that. Yeah.
I can't remember what the slide number was, but I think it was all the data sets, the knowledge graphs that you've done experiments with, and there is, if you could go back to that, there is a Wikipedia one where it states there's not enough memory because it's too huge.
Yeah.
Is that all? I mean, you've done experiments with all these?
Yeah, we've done experiments with all this. Okay. But I didn't say that we did experiments with all the existing knowledge graphs. No, we just, I mean, if you look at this table, you can just see that we tried to use various cases that could also have particular characteristics. For example, we have in the middle there the one called bank, specific knowledge graph that has only one class. So we wanted to see how the algorithm behaves in these cases and so on. So it has different, yes.
And domains as well.
Yeah, but this is agnostic to the domain. We don't really care what the data describe.
I have another question. You say that you will have around two, so it's very difficult to evaluate the graphs, actually. Have you tried to do the opposite, like using your graph as a ground truth and try to add some noise to the graph and see if your algorithm is capable of going to the ground truth again or something like that?
Yeah,
it makes sense.
We did something like that, but because like this, you only have artificial data. It kind of works well because we are based on what is important at the instance level. So even if you noise up your schema part, your ontology part, it will clear it out easily. Where we have problems is what I mentioned about the hierarchical relationships. Because you could have cases where you have an instance that is an instance of class B, which is a subclass of class A. So the instance is instance of both classes because of inheritance. And in these cases, you might, for example, the algorithm might find only the one of the two classes and miss the inheritance because of that. Okay, but it depends on the statistics. It depends how many subclasses are there, how many instances in each one. So it's okay. Anything else? Okay, so moving on in the next type of work, which deals with opinion and mining and sentiment analysis. And this was part of a European project that I had a couple of years ago, which was dealing with airport noise. Okay, so as you see, I do diverse things. So what was our problem there? We wanted to understand the level of annoyance, or if you like, more generally, how people perceive quality of life when they live around airports. Okay, that was the question that we were trying to answer. So traditionally, people were doing that by doing surveys. Okay, in the project, for example, we also did a survey. We also had a mobile app to survey people to be able to input that now at 12 o'clock I'm very annoyed and so on. But we also looked at Twitter specifically to try and understand what they are posting online, how much they complain, and so on. Okay. So if you would like to generalize a little bit the work was also a study on how much we can rely on social media to understand the opinion of people per se. Okay, you all know Twitter before it was destroyed by Elon Musk. So the work was done at that point, okay. And another interesting problematic that was not, of course, previewed when we started the work and the project was that during that period, COVID happened. So one quick, let's say, question could be, who cares about COVID and airport noise? But we did. And if you think of it, it's very easy to see why. Because due to COVID, what happened to airports? There was no traffic. So no airport noise. So nobody complaining on Twitter about airport noise. So one good way to destroy my project. Okay. But So what we did and what I'm gonna discuss briefly is that we did two things. So we did pre-COVID, we worked on methods that would assess in real time tweets that would appear discussing the subject. So tweet comes, we have a machine learning model. It takes it, classifies it, and tells us if it's, let's say, negative, positive, or neutral. Of course, this at some point did not make sense anymore, and we had to deliver also something more concrete for the project. So we went back and worked offline. So we downloaded tweets for the previous 5 years, for example, and we did similar work to classify them. The difference between the two is time and size. So the first solution is supposed to work fast and classify one post at a time. The second solution can be slower and classifies everything together, which at the end was very interesting because we were able to compare the two and see what different things we could make. We applied different methods and so on. Okay. Now, generally speaking, there are three problems that we need to deal with, regardless of the method, to make the final decision. Okay. Again, the final decision is related to if people are annoyed or not. So the first problem is what is relevant, right? So not all tweets talk about noise at the airports. Actually, not too many, on the one hand. And actually also this problem is important because if you misclassify something as relevant or not, it actually destroys your next steps, right? Because you then analyze something that might be useless. The second part is the sentiment analysis. So we are saying if something is positive or negative or neutral. And there are interesting problems that were also mentioned the other day we were discussing, right? So, for example, how you deal with abbreviations, okay, especially take into account that social media like Twitter have also their special lingo, right? People abbreviate there a lot. There are a lot of misspellings because we write on our phone and we walk and drive at the same time. There are incomplete sentences. Important things are negations as well, right? And more. So I'll make some points around that. I'm just mentioning that to say that the problem is more complex than just taking an algorithm and say positive, negative, and we go away. Okay, and then the third thing that we did is to do a statistical analysis on our results and try to see how they fit in space and time. Okay. So moving on a little bit fast. So this is the first solution we employed to train a model to do real-time classification. So as you see, only that is quite complex, right? So we do the pre-processing, then we try to classify the tweets as relevant and not relevant. So first classification, and there we used different types of classifiers. We ended up with a supervised machine learning algorithm. Then we did a second step of pre-processing to allow us to work for the sentiment classification, where we finally used SWN, a senti-word-net algorithm anyway, to classify that. This was quite difficult, as I said, to train because having the data, so it took us quite a long time to collect enough data for the positive case and actually manually to say that it was positive and then train the algorithm and so on. And then we did also some analysis that I'm gonna talk about that later on. So, okay, I'll skip the technical details, but if you are interested, tell me and I can elaborate more because it's a bit too much and maybe also too mathematical, so you might not enjoy it too much. Okay, so we did some temporal analysis trying to identify if there were particular hours in the day, for example, where people were complaining more or particular days. For example, one result that amazed us was that people were complaining less in weekends than in weekdays. I was expecting the opposite. And one possible explanation was that a lot of people go around the airports for work, so they don't live there. So they are not annoyed during the weekends. We did also a special analysis to try and put, yeah.
Do you use the time and the day only for doing like this graph, or also you use it as an input information to the system in order to then classify into positive and negative?
For the classification, because the classification, this part was real time. I mean, we trained the model and then we used it to classify in real time the tweets. The time did not play a role there because we were classifying tweet by tweet.
Maybe because I was thinking about it because as you said, the people is more annoying. Nice.
Yeah. But you see, for example, people are quite annoyed. If you see the top graph, people are quite annoyed during the morning and during the evening, which is a normal case when they wake up and when they go back home or they leave work and they want to relax. And there are some more results later on at a larger scale. So, okay, temporally, we try to understand what's going on. In that case, the results were kind of expected. You see that there are two main, let's say, centers of annoyance, which are around the airport and around the main corridor that is there. Okay, and then in the second, in the offline case, okay, what we did is that we gathered the tweets historically. So we went back, I don't remember now exactly, 5 to 10 years or something like that. So we got more than 2 million tweets to work with. And we also took information from other sites, like, for example, Airbnb, where people also go and complain. I mean, I booked that and that was bad. Right. There we followed a little bit of a different process, but not very different. So again, pre-processing relevance and sentiment analysis. It's just now that we used for the sentiment analysis different methods based on neural networks. And we try to solve different kinds of problems. For example, here, one problem that we had is with what we compare to establish relevance, for example, what makes something relevant. So we experimented with that, and we actually we used different methods, right, based on different types of embeddings at word level, at sentence level, at the document level. Embeddings, if someone is not familiar, are ways to represent textual information as vectors, right, as mathematical structures. So then we can compute more easily on top of them. Okay, long story short, a lot of experimentations for the relevance part with different types of neural networks to choose the best one. A lot of experimentations for the so you see here, there are different things to decide, right? So we were trying to decide how we compare, what kind of similarity function, what kind of similarity thresholds we are going to give, what kind of embeddings we are going to use, what kind of algorithms for classification with those embeddings for the relevance part. Okay, so a lot of experiments there to decide what's best. For the sentiment analysis part, again, a similar idea. Okay, different types of neural networks we used. We ended up with what we decided was the best, which was actually a convolutional neural network. Okay, so not something very complex, although we tried very different complex architectures. Okay, not to go into the results. So at the end, we did a more detailed analysis because we had historical data now, so much more data on the annoyance, which revealed some kind of interesting results that nobody really could explain at the end. For example, you can see there on the map that these orange lines are the noise contours that the airport has, because every airport is obliged by law to provide an idea of how far at a specific decibel size will reach in the area. So you see that while it's there, so that's the orange part. We have users that appear all over the place, so which means that the noise affects communities not necessarily very close to the airport. You see the negative to its distribution, so annoyance, which is generally consistent with what we expect, with just an issue on the lower right part. You see there is a community that seems to have a lot of problems that is not very close to the airport, and neighborhood communities that are closer have fewer problems. Okay, we don't know why. I mean, we discussed that also with the Heathrow people, and they were equally amazed.
Maybe the population is not or not?
No, I mean, we normalized that, but I was expecting that you're going to say maybe there are grumpy people living there, which could also be the case.
Yes.
Something so close to the airport, you assume that you are going to.
Yeah, that's true as well. Yeah, but that's very difficult to capture. Okay. Another interesting part was the temporal analysis that showed that you see that interactions increase over the year, but negativity increases quite a lot, okay, which is kind of expected. Another interesting result was that we identified that, for example, the biggest annoyance appears in March. You see the x-axis there are the different months of the year. And this was explainable because in March, charter flights and anyway holidays flights start, so the traffic increases quite a lot. So annoyance goes with that, and that's an image consistent over the different years as well. What else is interesting? The distribution by day verified the previous results that during the weekdays we have more issues than during the weekends. And overall, I mean, our conclusion, if you like, was that okay, that was really a lot of work, but now we have a really good understanding of what works, what does not work, where we should pay good attention, and also that we have results that were not really captured by the more traditional methods. And that was quite interesting for the people we were working with, because it gave them various insights that were not evident otherwise. Okay. Another work that we did with some colleagues also from Argentina was working on trying to track the political discussions that happened before the elections. So I will talk about a work that we did that concerns Argentina, because we had data from there, but we did also that work for France recently, and we published a paper, I think, some months ago. So let's try to define first a little bit the problem. Okay. So what we have, as I said, are discussions about elections, okay, in Argentina for 2 election periods in 15 and 19. And what we are interested in is to measure similarities basically across different political parties. And we want to do that because like that, if you have an election, and this was the case there, that goes in 2 rounds, okay, then in the second round, you usually have the two, let's say, most popular parties that advance. And then who wins depends on how the other parties behave, right? Or the voters of the other parties behave. And in Argentina, in one of those cases, the results were opposite than what it was expected. So that started the discussion on how we can track that. And the idea is to try and see if we can explain this by looking not at what the parties officially say, but how the voters react in different discussion points online, and try to see if this explains, for example, why a voter that voted in the first round left party will vote in the second round for an extreme right party and mess up the results that we expect. Again, it's important to say, we are not trying to predict results of elections, right? So unfortunately, because that has a lot of money. Okay. So what we did is that we captured the data of the discussions online. You see that we have really big numbers, 50 million tweets for the one case and 280 million tweets in the other. So we are hoping that this gives us enough material to really validate what we do. And what we did is that first we tried to define the topics of discussion. And for that, we took the hashtags of the tweets and we create communities of the hashtags, not of the users. And if hashtags belong to the same community, we do a kind of topic modeling and we assume that they belong to the same topic. So then we use these topics to track the users, track what users are discussing. Okay. So we characterize users based on the topics that we are discussing. We have a vector that represents the user, and then we assign a user to a political party. Very simply, if the user is active in retweeting what the party says. Okay. Of course, there are problems there. For example, users might retweet multiple parties and so on. So there we take the majority part. But okay, I mean, we solved that quite well. So then what we do is that we compare the vectors of what the user is discussing and what, let's say, the whole data set is discussing. And we try to see where the user belongs to, right? So like that, we can classify, we can compare the users and classify them at the end. So like this, we can assign the users to specific political groups. And then based on what the users are discussing, we are trying to track how coherent are the discussions inside the group and between groups. Okay. So we use what we call self-similarities. Okay, so similarities between inside the same group and between different groups. So you can see there how discussions evolve for the followers of the different parties over time. And you see already that different parties have similarities or not, right? You see peaks that are the same for all the parties, which means that are subjects of common interest, and others that are specific for the party at hand. You see the positioning of the different parties, and the black line in the middle, if you can see that, is the general opinion. So let's say the average opinion of everybody to be able to compare of how it goes. So like that, we can track closeness of political parties, even if they are not, if you like, or they don't claim to be ideologically close. And you see how things change after the primaries. They have that in Argentina as well, like in US, the primary election between inside the same party, then the first round, okay, and so on. So, for example, like that, we can explain differences between the first round and the second round. Because for the four parties that are, sorry, for the three parties that are there, you see that the lines depict the comparison between the parties in pairs. And like that, you can see that what is similar and what is not, right? So, for example, we can take the yellow line that you see there, and you see that when things are around zero, the opinions are very similar. When they become positive, they become different. When they become negative, they become different on the other side. And you can see how things track, right? So you can see that comparing, for example, the right party with the left party that lost in the first round can explain why the right party at the end won those elections, right? Because those who were in the who lost the first round, did not go to support the other left party that advanced in the second round. Okay. So we did that quite extensively. We tried to do comparisons in specific time periods to track specific also subjects, okay, and so on. We tried also to look in how robust the communities that we created. Again, these were semantic communities trying to track what people are talking about, not user communities. Okay. And we did more work on that. For example, we now have a method that does that without having to look into the whole past, as it was this example, but looking in the last month and updating somehow in real time this kind of comparisons and so on. So we tried to show that you don't need necessarily to process the whole data set every time, because that's too big, right? And that was, again, one of the problems that we had. Any questions before I move yet again to a completely different subject? And thanks a lot for the coffee.
How can you evaluate that? Or in a way, to know if you are doing it right or not? I think it's very difficult to.
Well, we are doing it right mathematically. Okay, that is provable by the method we are using. I mean, the way you define the inter and intra similarities are mathematically okay. What conclusions you draw, though, is a very big question, right? And that was discussions that we had also quite extensively with the reviewers of the papers that we published. Because it's not one way to see things. Some things also rely a lot into understanding the local situation correctly. So yeah, and that's why I said that while one could use that, right, potentially to track the discussions and, for example, try to predict what will happen in the second round of some elections, that's not advised. I mean, it's not what we do and not what we claim. I'll try to be also fast. So that's a very recent work that we did on explainable recommendation systems, right? So first of all, I hope everybody knows or uses a recommendation system, and I'm sure that everybody uses it even if he or she does not know. Okay, so from Amazon to Netflix and wherever else, you get suggestions of what to buy and what you see, right? So one question that appears is why we get those suggestions. So we need to get an explanation. But what we actually worked on in this case was why we don't get a specific recommendation that we would expect, right? For example, I'm a computer scientist. I would expect to get recommendation for computer science books, but I don't. Okay, why is that? That's a more difficult question than the direct one, because as you can imagine, the search space that you have to find this why not explanation is much bigger, because it could be for many different reasons, right? But why you get the recommendation is more straightforward, because you follow the way the algorithm works, right? So what we tried to do here is to provide what we call why not explanation. So why an item or a category of items is not in the recommendation list, or if you prefer, is not ranked in a higher position, right? So why do I get this in position 15 and not in position 1, for example, right? And that has quite different uses, from, providing explanations to the users, from debugging the system, because it could be an error that I don't get this recommendation, and also providing transparency to how things work. Okay, so quite fast, our input is a heterogeneous graph like this. Okay, as I told you, I like graphs, so there it is again. Heterogeneous because it captures different types of information, users, items, in this case, books, and categories of books. Okay, so we have different types for the nodes. What we used is what we used as a recommendation system is an algorithm called personalized page rank, which tries to find the important nodes to recommend based on the connections that exist. So basically, more connections, more important the node, fewer connections, less important, to put it very simple. Okay. I'll skip the mathematical problem definition, but we can stick to the more verbose one. For example, you have your books and you want to know why the recommendation algorithm, the recommendation model did not give you Harry Potter. Okay. There are two ways that we work. One way is that we explain by adding. We say that if you want, for example, to get Harry Potter, you should have read that book, or you should follow Dimitris, who have already read Harry Potter, and or we work in a remove mode and say, okay, if you had not read that book, then Harry Potter would be more important, so you would be recommended that. So you need to, we suggested that you remove something from the graph. Okay, so we have a framework that allows you to use one, the other, both of them together, and so on. And that's the basic idea, right? So you have your recommendation that is, okay, you're a computer scientist, so I recommend you a book about Python. You say, no, but I'm a computer scientist, so I would like to read The Alchemist. Why you don't recommend that? Then you start by working on that. You measure, okay, so basically you remove everything, right, in the remove mode, and you say, okay, what do I need to add so that now I can get the recommendation that I want, right? So I keep adding, okay, at some point I get now what I wanted as the new recommendation, and which links have not been added basically in the graph back. I consider them as the explanation that I provide to the user and say, okay, if you want to be recommended The Alchemist, then you should remove this link and this link. For example, you should not have read this book or that book. Okay, of course, okay, again, you can very easily criticize, and I'm saying that myself, saying, okay, what's the point of recommending to someone not to read a book, right? You cannot go back and unread a book, but that's a different problem, okay? Okay, so we evaluated that with different data sets to be sure that it works quite well. We have, you see, a set of algorithms, not only one, that provide us this kind of explanations. We evaluated that based on the size. For example, generally the literature says that people prefer short explanations than very large ones. So we tried to go for minimality. We also used the time because that's again very computationally expensive process. And the success rate, because not all methods provide the results in all cases, right? As you can see, we have algorithms that give you an explanation in, let's say, 10% of the cases, because it's really a very hard problem to work with. Generally speaking, this kind of work, though, is really important in all kind of recommendation systems, and not only, and all kind of AI models that we are using nowadays, right? To be able to explain why I get a result or why I do not get a result is very important, is very hard, and still at the moment, the work that we have cannot guarantee explanations in all cases and for all models. Okay, so there is now a lot of work in the area. It's one of the hot topics in AI if someone is interested to work on. If you are more interested in that, we have a GitHub site that you can look at. We have there the papers we did. We have also a demo application that allows you to play with the different algorithms and so on if you are interested. Moving on to recent research projects. Okay, so I will start by mentioning one very big project that we started almost a year ago, which is the ECOS project, the European Cloud for Heritage Open Science. Which is the mission that the mission of this project is to build the European Collaborative Cloud for Cultural Heritage, which will be a platform shared with the ability to facilitate collaboration for different types of users, professional, researchers, students, okay, and so on, and share not only data, but also applications, services, resources, training, okay, and so on. So the main aspect of the project is to build an open source infrastructure that could be able to survive also for the future. Taking a more holistic approach. We'll talk about that in a minute. And at the end, create also a legal entity, so to be able to sustain what we create for the future. It's a really large project. We are running for 5 years. We are across, the members are across 15 of EU countries, 16 now, sorry, because we expanded one. We have 53 partners now, of which 16 are umbrella organizations like museum associations, scientific and infrastructure entities like DARIA, IRIS, and so on. This means that we federate more than 1,000 organizations, which makes exchanges and management quite a nightmare, but that's my problem not to solve. Okay, so the idea is that we interact and we serve at the end a huge variety of disciplines, which are all under cultural heritage, but do not necessarily speak to each other. As I said, we have a set of umbrella organizations that hopefully will help us a lot doing that. because reaching individual organizations is quite difficult. So you see there people that are working in languages, in digital humanities, in archaeology, okay, in many things. This is part of a large effort by the European Commission to support cultural heritage in Europe. So the first, let's say, call for proposals that where we applied for was in 23. So the project started in 24. There it was only one project funded for the platform, us, and 3 other projects funded to create tools. Then there was a call that opened last year, and the submissions were in January 25. The results are not out yet. You see the second phase of where we expect to have 10 more projects. Then there is a third phase that is announced now, was announced actually yesterday. And the deadline, I think, is in September, where more, I think, 10 more projects will appear. And that's important because all those projects are required by the Commission for maybe the first time ever to build on top of us. So we have to provide them the infrastructure to build their work. And that's also a very difficult task by itself because the projects have their own, structure, their own timelines, and so on. And they are asked to build on a project that just started as well. So it's quite complicated to go along. So at the end of the day, there would be something like 20 extra projects plus us for a total of 110 million euros that is supposed to be fully in place by 2029. We are going to support different levels of integration, of course, so nobody is required to integrate at the same level. Our effort, though, is to be able to share things correctly. And for this, we also align with different initiatives like the data space for cultural heritage and other data spaces that are around, Europeana, for example, that you might know more, and so on. So the idea is that we'll provide something that would be a gateway to all that at the end. And we want to build a kind of a digital commons environment that is based on what is generally called a heritage digital twin. I'll give a little bit more details about that as well, more technical information. So that we create a shared space for everyone that can not only be there and share data, but actually work together with others. We try to do that, and we work quite a lot on with the communities. So not a top-down approach, but a bottom-up approach. And we will try to offer different services for that, like, for example, a single entry point where you go and you authenticate yourself once. We are going to work on issues around data quality, around data provenance, right, and so on. We are going to provide a few tools already with our project. For example, a tool for annotating 3D structures, 3D images for conservation and restoration purposes. A virtual transcription lab that would allow you to scan OCR and then process different texts, right, from different periods, and then also an ingestion tool that would allow you to more, let's say, rigorously and in some way more visually to describe semantically your data. We have programs, and this might be also of interest, of cascading grants. The first one just closed yesterday. But there are more that are coming. One will come in September 25, one will come in January of 27 with different focus each time, but still building things around the cloud. So if you are interested, we can share the information and would be happy to have you participate also. Okay, the money is not big, but it gives the opportunity to produce something and put it in the platform, which would allow for really increased visibility and increased possibilities for collaboration with other actors. So I think it's quite interesting. What you can contribute to, if you like and you have the time, and we would greatly appreciate that, is that we have a questionnaire online that tries to understand what you need from the cloud. So if you can provide some insights, either individually or as representatives of organizations, would be great as well. And we will, process that and share the results later on. And further on down the road, we will have different workshops that we will invite the communities to also participate and provide input on how we are doing things. A few words for the more technical parts. First of all, we are doing a lot of work in the conceptual modeling part. We will provide a high-level ontology to describe what we call heritage digital twins. In general, a digital twin is a way to say that we have a holistic information about a heritage asset, so everything that comes from different sources, from different people, and so on. And we are able to combine that, and that's quite important to be able to learn additional things. So we are going to introduce at the end of the project a digital continuum where you share something, stays there, gets reused, gets changed, gets advanced, updated, and so on through the technical environment that we will provide. The setup is quite complex because we want something that will survive for the next many years. So we are not building something that will work for 1 or 2 years, but at least for a decade or more. And we want to be very flexible. So we are looking into distributed solutions and federated solutions for processing and for storage. We will connect to different, as I said, existing initiatives like data spaces, like existing online aggregators like Europeana and so on. We will provide a single entry point where users will be able to authenticate and get authorized once. Will be able to have their personal user space with their personal applications and services that they prefer to use. We provide necessarily security, access management, who can see what, right? Because although the idea is to work with open data, we don't want to exclude the people who have intellectual property rights to contribute to the platform. So we need also to have some access management in place. We also will have in place monitoring because we need to understand what is needed, how the cloud is used, what kind of processing resources are necessary. And then we will build on top, as I already described, the different applications that are coming from the EU projects, the cascading grants, and so on. Okay. As I said, we are going to build a conceptual model which we'll use to provide a high-level knowledge graph that would be the entry point to all the data that we will have. And there we are going to build some AI-based methods to be able to find similar data sets, so similar in terms of the knowledge graph, to suggest to the users automatically, to be able to also assess semi-automatically, because fully automatically is probably not possible, the quality of some data and metadata that we are going to have. And all that we want to be extensible. So if someone wants to come with his or her own data and say, okay, I have my triple store, I have my equipment and I want to join, we are going to provide the requirements and best practices so you can actually join the cloud. We don't strive to get everybody's data or metadata ourselves, right? We want not to care about that because it's both difficult, but the main issue is that it's not flexible. And because we expect more organizations and people to be added in the future, that somehow helps us to solve this problem. So based on that, we will also provide descriptions for, as I said, data quality, data provenance. Also, we want to capture workflows because it's important to be able to share workflows between communities that I think will provide a lot of value added. So at the end, the idea is that we build a platform that is pan-European, that provides ways to manage knowledge, to use that to foster innovation, and to support the work of the community. So an ideal world would allow us to move everybody's work to the cloud. Okay, I don't expect this to happen fast and next year, but we hope that this will happen quite fast. We hope. That also brings me on to some, let's say, personal interesting research issues. For example, this means that we want to work a lot on distributed knowledge graphs, which is a problem by itself. If you add on top of that issues of privacy and intellectual property rights to be managed somehow automatically, this adds to the complexity of the problem. But if we have the knowledge graphs distributed, then we are interested also to distribute the learning that we do on top of them. So another area of interesting problems. And then also interesting things, some of them we discussed as well already, is that an interesting thing is to use, for example, AI, LLMs, for example, as interfaces between humans and the cloud. For example, you want to search for a data set, you ask the LLM to give you, to do the query for you and not bother yourself for learning a query language or anything else that might seem too complex. That's work that picks up a lot of interest in general. So already there are SQL to text interfaces. But we can do that also for SparkQL, for example, for the semantics, for the knowledge graphs as well. So that is a project that for the next at least 5 years, but I hope more, will take a lot of my time and effort. And I hope the result would be satisfying for everybody. If you want more information about the project, the website and so on is there. You can follow up. We have a newsletter that you can subscribe to if you want to get the information more punctually, and deals with, and that might be also of interest to some of you, deals with the problem of how information flows from science to bad science that we see today. Take the example, for example, of climate change, or the example of COVID vaccines, how we started discussing all that, and then how the discussion became a fight between, vaccines will kill us all or will save us from the pandemic. So we're trying to track how this happens on the discussion online, how we change from the one place to, from the scientific part to the pseudo-scientific part. And I do that with colleagues that are in communication and information and media studies. What is interesting for me there, though, and I'm only showing that, is that I'm working, or I will be working more precisely, to provide what we call argumentation models. So a way to extract and describe arguments about a subject. So what is in favor, what is against, what came first, what came second. And we want to produce a semantic model out of that, and then to be able to reason on top of that with AI or anyway more standard reasoning tools we see. And that's a more general idea to apply in other discussions, right? So that interests me quite a lot, because for me it's the next step in the research area that includes sentiment analysis that I was describing before, opinion mining, and so on. This is a much stronger way to capture discussions, because you actually understand who is talking about what and what he's saying. And last one, I think, is a project that tries to understand how we make our lives more sustainable, especially in large metropolitan areas, where the basic idea is that we try to reduce, for example, emissions, okay, and all that. But what has happened is that there has been a paradigm shift after the pandemic. People started moving more to the suburbs because during the pandemic, they realized that being, let's say, confined in a small apartment, especially in Paris, for example, where small is really small, is not really a good way to pass your time. So they started moving away. This was combined with the ability of remote working that became at some point, now it's changing back, but it's still quite strong, a strong tendency. So then the question is, can we find interesting new patterns that are there? Can we see how people are moving around, and if these new patterns contribute more to the sustainability or not of what we are doing? And this changes quite a lot. I mean, what we're trying to do is we try to change how people in transportation work, because so far, anyway, they're working by building agent-based models to simulate the situation. So now we try to introduce AI-based models that would allow us to do predictions based on that data. So any questions if you have at whichever of the subjects, happy to discuss. If you need to contact me, you have my data, but anyway, it's still here. And thanks a lot for your patience for almost 2 hours. I think it's maybe the longest talk I've ever given. So.